Okay, our next topic, we've computed some moments of the exponential distribution, but we're going to specifically focus on moments of the exponential distribution here. Okay. Ooh, getting a little sloppy here. Okay. So first thing to do is that I want to define the gamma function. So for a real number, R positive, the gamma function is defined as integral from 0 to infinity x to the power r minus 1 e to the minus x dx. Okay. And there are a few special cases that we highlight. One is that gamma of 1 is integral 0 to infinity e to the minus x dx. That's 1. Another is that gamma of r plus 1 is equal to r times gamma of r. How do we see that? Well, we can see that by first writing the definition and then integrating by parts. And if we do that, what we'll see is that this is equal to r gamma r. In particular, if r is an integer, then gamma of r plus 1 equals r times gamma of r. Gamma of r is equal to r minus 1 times gamma of r minus 1, and so on. We end up with r factorial. So gamma of r plus 1 is r factorial. And when we work on half integers, we've seen up above, actually, that the calculation we did here we can show that this can be expressed in terms of the gamma function on a half integer. Gamma of 1/2 is square root of pi. Gamma of 3/2 is 1/2 times gamma of 1/2. So it's square root of pi over 2. Gamma of 5/2 is 3/2. Gamma of 3/2, which is 3 square root of pi over 4, and etc. Okay. And this is how we can calculate the moments of the exponential if we let x be a standard exponential. Then expectation of x is integral from 0 to infinity of x e to the minus x. This is exactly the gamma function with a parameter of r equal to 2, right? Because it's x to the r minus 1. So don't So it's x to the r minus 1. So this is gamma of 2, which is equal to 2 minus 1 factorial. That's just 1 factorial. 1 factorial is 1. Expectation of x squared is x to the x squared e to the minus x dx. But this is gamma evaluated at 3. This is now going to be 2 factorial, right? And the variance of x is expectation of x squared minus the expectation of x quantity squared. So that's 2 minus 1 squared. That's 1. And just in general, the expectation of x to the power r k can be expressed as integral x to the k e to the minus x dx, which is gamma of k plus 1, which is k factorial. So then if we were to let t be exponential lambda, then we know that we can express t as equal in distribution to x over lambda. And in this case, expectation of t is equal to expectation of x over lambda, which is expectation of x quantity divided by the divided by lambda, which is just 1 over lambda. Variance of t, which we've calculated before, is the variance of x over lambda, which is just the variance of x over lambda squared. And we know the variance of x is 1, so it's 1 over lambda squared. And then in general, the expectation of t to the power k is equal to expectation of x divided by lambda to the power k. We can take the 1 over the lambda to the power minus k out, and we're left with expectation of x to the power k. What we get is k factorial over lambda to the power k. Okay. So anyway, those are some nice ways to calculate the moments of the exponential, is that we don't have to do the brute force integrals by realizing that we have this function, the gamma function, and by exploiting this property, which we were able to derive by integration by parts. This is really extremely valuable and extremely useful. And by having that function, it allows us to derive these moments very easily. This gamma function, by the way, the presence of this gamma function, this is why in the gamma distribution, we wrote the normalizing constant in that way, even though the gamma, we just at that time wrote that gamma of r is r minus 1 factorial, which we now know to be true. We expressed it in terms of the gamma distribution because technically the gamma distribution does not require r to be an integer. It can be defined for any positive value of r, and where the gamma distribution gets its name is by the presence of the gamma function in its normalizing constant.